Kuboyama. It's from Tokyo Tech, and he's also going to give a next lecture about the characteristics of polymers. Let's welcome Professor Kuboyama.
Thank you. My name is Keiichi Kuboyama. I'm an assistant professor of Tokyo Tech, and I have been collaborating with Professor Ogisawa in the same field. So I'm in charge of the second part of this lecture. Okay. And the second lecture is about the viscoelastic property of polymers. The polymer has a viscoelastic property. So viscoelastic means the viscous and elastic properties. So polymer has both properties. So we call such a property as viscoelastic. So for example, when you think about a chewing gum, so when you elongate the chewing gum slowly, so the shape changes. And when you release the stress, you can maintain almost a shape and doesn't return to the original shape. That kind of property is called as viscosity. And when you change the rapidly, so the chewing gum returns to the original shape. That is elasticity. And such a phenomenon depending on the speed of the deformation. So the time speed is a very important factor of the property. So maybe now it's so I'm sure the phenomenon like this. This one is not the chewing gum, but the low rubber material. And when I hold on, it's difficult to show you. When I pull this one rubber material slowly, so the shape changes like a chewing gum. And when I release, some part return, but some part doesn't return to the original shape. So that is shows the viscosity and the elastic property, both of them. And so at first, let's start from each component. So at first, let's discuss about the elasticity. So I'll introduce the behavior of ideal elastic material. So when you think about the, okay. Sorry. Such kind of polymeric materials. Polymer, if there is a bar of the polymer, and when you elongate this bar, and the original length is L0, and the first surface area is A. And after you elongate the elastic material, so elongation becomes DL. In that case, you can define the stress as a load over area. This means load applied per unit area, and the strain is elongation over initial length. So this one is the ratio of the elongation. And in this case, if you think about the ideal elastic material, that can be represented as a spring. So spring, maybe you know the behavior of the spring. So when you draw the strain stress curve, this becomes like this. So stress is proportional to linear to strain, and the slope is elastic modulus, and the equation becomes like this: stress equal elastic modulus and times strain. So please remember this. This one is stress, and this one is strain, and this one is elastic modulus. So this equation is very similar with Fuchs law. So this one is spring constant, and the elongation and force. So maybe you can easily remember this equation. And next, when you apply this constant stress to this spring, the strain also becomes constant value. And when you release the stress from this spring, the shape of the spring becomes original shape. So the strain becomes zero. This one is the typical behavior of the spring. So next, let's think about the viscosity. What is viscosity? So viscosity is resistance to fluid flow. So let's think about when you put your hand in the water bath and move it to the forward. So when you during you moving your hand, you feel the stress on your hand. But when you stop your hand, you don't feel the stress, and the shape of the water doesn't return to the original shape. So such kind of phenomenon is shows the viscosity. And kinetic energy used in this process is converted to heat by internal friction with the water. So in such a material, viscous material can be represented by dashpot. Do you know dashpot? So for example, dashpot can be represented by such kind of device. So this one is a container include filled with a liquid, and there is a piston, and there are small holes. And please imagine that when you pull the rod this direction, so can you move this piston? Maybe it's difficult because the hole is small. So you can slowly move the rod. But you cannot move this one rapidly. Okay, so such kind of device is called as dashpot. And viscous material can be represented by such a sign. And in this case, stress when you apply the tensile force to this rod can be expressed by this equation. So in this case, as I mentioned in the case of the water, so the force generated by the stress is not proportional to the strain, but to the strain rate. When you move the rod, during the rod, force is generated, stress is generated. So in the case of viscous material, the stress is generated by the strain rate, and that is proportional to the stress, like this. And when you plot the graph like this, x-axis is strain rate, and y-axis is stress. So strain rate and stress is proportional, and the constant slope is viscosity. So the difference between the elastic material and the viscous material is this part. Please remember that. That one. And when you apply the strain gradually. That means apply the strain at the constant speed. So stress becomes constant. But when you apply the constant strain from here, so stress becomes zero because here the strain rate is zero. So I explained that in the case of elasticity, stress is generated due to the strain. So the stress and the strain is proportional. But in the case of viscosity, stress is generated by strain rate. So stress is proportional to strain rate, and the constant is viscosity. So if in the case of the polymer, elastic and viscous property, both of the properties are included. So generally, if you apply the high strain rate, so this becomes more elastic. Yeah, because as I mentioned around here, you cannot apply the rapid strain for the viscous material. And when you apply low strain rate, the force to the material low strain rate, so it behaves like more viscous material. And at what strain rate does it change from viscous to elastic is relaxation time. So behavior changes from elastic to viscous, and relaxation time decides the behavior. So I'll explain more in detail later. And from here, until here, I explained elastic material and viscous materials behavior. And let's think about the viscoelastic materials from here. At first, please think that if you load the constant strain to the perfect elastic material, so the stress generated in the perfect elastic material becomes also constant because the stress is proportional to strain. So please think about that in the case of perfectly viscous material, how it behaves when you apply the load at when you apply the constant strain. So please think about the plot of the stress in the case of the viscous material, and plot the graph, draw the graph on your notebook, or if you don't have the notebook, please think about it in your mind. So I'll give you 30 seconds to think about it. Please think about it. What kind of graph you can draw for viscous material when you apply the constant strain? Like this? Okay, so I'll show you the answer. So this becomes like this. So because when you stress in the case of the viscous material is proportional to the strain rate. So strain rate of in this one is at the 0 second is very large. So if ideally it becomes infinity, but in the real case, this one doesn't reach to the infinity, but becomes very large stress. And after that, strain is constant. So the stress becomes zero. This one is perfectly viscous materials case. And so if both properties are included in a material, what kind of behavior you can see? So this one becomes like this. So stress becomes high value, but after that, stress continue to decrease and approaches to a certain value. So this phenomenon is called as relaxation phenomenon. And in this case, stress relax. So this one is stress relaxation. And the time, so the stress becomes 1 over E. In this case, E is base of natural logarithms. So this time is called as relaxation time. Okay. So now, when you apply the constant strain, relaxation process occurs. Relaxation process can be observed. So this means maybe, yeah, if you, this is face-to-face lecture, I'll give you the laboratory materials and you can test this phenomenon by yourself. But now, this is online, so I can show you only in my camera. So for example, when you, so let's think about the chewing gum. So when you elongate and maintain the constant length like this, so this part continue to elongate, even if I maintain the length of the laboric materials. So the stress I feel becomes lower, like this. Can you see the shape of the laboric material change and break? So okay, so to such kind of phenomenon is stress relaxation. And this process can be represented by such kind of model, combination of the spring and dashpot in series. And in another case, for example, when you apply the constant stress, so in this case, creep phenomenon occurs. So I'll explain more in detail later. And such a phenomenon can be represented by such a combination of both component in parallel. And in this case, okay. So at first, let's start from the stress relaxation process by modeling with in series. And this one model is called as Maxwell model. And when you connect each component in parallel, this model is called as a forked model. So strain relaxation and creep phenomenon is a different phenomenon. So for each phenomenon, we can make different models to explain such a different phenomenon. So let's start from the Maxwell model. So Max model is a model for the constant strain. So initially, you apply the constant strain. So rapid change occurs. around here. In this case, when you think about the deformation of the spring can easily deform. Yeah, because the stress is generated from the strain and it is proportional. So rapidly stress of the spring part changes. And when you think about the deformation of the dashboard, so when you apply the big strain to the dashboard, strain rate becomes very big, very large. So in that case, stress also becomes very large because stress of the dashboard is proportional to the strain rate. But it is very difficult and this process is it's not possible, impossible to occur generating such a big stress. So just after when you apply the constant strain, only the spring deforms, but dashboard doesn't deform. So the generated stress is come from only spring part. But after that, when you maintain the strain length of this part, so the spring stores energy, and the spring continue to pull the dashboard. So dashboard can move slowly. So the length strain at the spring part becomes lower. So the stress continue to decrease. And this phenomenon is called as relaxation process, relaxation, stress relaxation. And when the stress becomes 1 over E is base of natural logarithms. So this time is called as relaxation time. So balance between elasticity and viscosity determine this relaxation time. So knowing the relaxation time is same with knowing the intrinsic properties of materials. So this relaxation time is very important property of the polymer. And the second part is this one. You can make an equation for this Maxwell model, and relaxation process can be expressed by the equation. For example, in this case, you can think about the strain for the spring part and dashboard part, because as I explained, the deformation of each part is different to each other. And total deformation, total strain can be represented by the addition of both components. And when you think about the stress for each component, the same stress are applied to each component. So this part can be, spring part can be represented by this equation, and the dashboard part can be represented by this equation, because dashboard part can be represented by the viscosity times strain rate. And when you combine both of them, you can easily make this equation. And when you solve this equation by using a initial condition, in this case, the strain is constant. So you can solve the equation like this. The stress, this one is stress at the time equal 0. And exponential of minus t over tau. Tau is relaxation time. So this one, this equation can explain this relaxation process. Okay. So next one is a creep model. Creep. Okay. So what is creep phenomenon? So please, can you see my video image? So when I in the case of stress relaxation, I maintain the length of the sample at constant. But in the case of the creep phenomenon, you maintain the stress, the weight at you should apply the constant weight to the sample. So for example, when you apply this lavalic material to about 1 kg, 1 kilogram weight, please imagine such a situation. The sample slowly elongate and continue to deform. No, okay, so it's difficult to show you such a phenomenon, but please imagine that kind of phenomenon. So, for example, in this case, this one is forked model, but please imagine that there is a polymer film and put the weight, heavy weight to the film. So film will elongate slowly and continue to elongate, and at the constant, at the certain value, the strain stopped. So this one is a graph of that phenomenon. When you pull the small weight, so the elongation occurs, but at a certain elongation, this one reaches a certain value. And if you apply the heavy weight, so sample continue to elongate, and finally the fracture occurs. So such a phenomenon cannot be represented by the Maxwell model. So Vogt model is used for represent such a phenomenon. In this case, you can also make an equation. So in this case, the stress for each part is different each other. And so the total stress is represented by sum of the stress for each part. And you can also make an equation for spring and dashpot like this. And when you combine all of them, you can easily get this equation. And when you solve this equation under the condition of the constant stress, in this case, constant stress, not the constant strain. So you can get this equation. So this one represent this curve. So by using this model, you can describe this phenomenon. Okay. So, and in this model, please think about the behavior of each component. When you apply the stress, initially this dashboard part cannot move rapidly. So when you so the starting point is 0 because you cannot deform rapidly this part. But after that, this one slowly elongate. So this spring part also elongate. So the strain becomes larger. So this phenomenon can be represented by this model. Okay. And this tau is different from the previous one. This tau is called as a time, and this tau is time constant, also time constant, but this one is called retardation time. This one indicates the time delay of strain, like this. And if the time is smaller than tau, smaller than retardation time, material behaves like elastic, this part. But if the time is larger than retardation time, so strain becomes very larger, then this one behaves like a viscous material. And if the time becomes very big, so reach the equilibrium strain, or in some case, the fracture occurs like this. So maybe you understand the polymeric material shows the elastic and viscous properties. And both properties very important to decide the property of the polymeric materials. And so let's think about the tire property of the tire and the management of the viscosity and elasticity. So if the tire, you know the tire is made by the rubberic materials. And if the tire behaves like an elastic material, so when you apply the force to the tire, the deformation occurs and the relationship between them becomes linear. That means when you apply the weight to the tire, the deformation becomes like this. And after that, if you deviating the sample, the force deformation curve is same with the increasing process like this. So there is no energy loss. So during the deformation, the energy is stored in the spring, but when you release the weight, energy is also released, and there's no energy loss. But when you use rubberic materials, that is not elastic, but this one is viscoelastic material. In this case, when you apply the force, deformation occurs. But in some part of the sample behaves viscous behavior. So during the deformation, the energy loss occurs. So when you release the load, the different path, the load deformation curve the load deformation curve becomes different from the initial one. And this area is energy loss. So in the case of the automobile tire, it is important to reduce the energy loss. That is important for making a fuel efficient tire. So so in the case of the tire, lower rolling resistance is important. And also the better braking performance is also important. When you stop the car, the braking performance is very important, but when you drive the car, the low rolling resistance is also important. But both of them are like dichotomy. So when you lower the rolling resistance, so resistance becomes low. So braking property performance becomes low, also lower. So it is difficult to realize both of the properties. But now the tire companies make excellent tires. So that is due to the frequency difference of the frequency domain. So this means that when you think about the rolling resistance, frequency means when you roll the tire feels vibration. So in that case, frequency is very important. And when you think about the rolling resistance, so the frequency domain of several tens hertz is important for this property. And if you reduce the resistance around this frequency region, so hysteresis loss becomes lower. So it is good. And when you think about wet grip braking performance, so this phenomenon is related with such a high frequency property, 10 to 6 power hertz. So when you improve the wet grip property of this frequency, so you can get a good braking performance. And if the rolling resistance of tire is reduced by 20%, so fuel economy improves by approximately 2%. This one is in the case of the general urban driving. So the fuel efficient tire improvement is very important for the energy and reduce the energy loss. So this one is a cross-sectional image of the automobile tire. So tire is made by many parts. And this part is tread part, very important point of the tire. And rubber is used this part. And normally natural rubber or styrene, butadiene rubber or butadiene rubber are used. And in this tire, the rubber is also used inside of the tire. This one is called inner liner. Normally, the IIR, that is also called as butyl rubber, that is used in inner liner. This one is for this material has high gas barrier, low gas. This one doesn't pass through the gas. So when you use this rubber as an inner liner, the tire does not lose air. So this one prevents the tire loss, gas loss from the tire. So this one is also important. But now let's think about the mechanical property, rheological property of the polymers. So in the case of tire development, there are some tire development issues. So Now let's think about to achieve both improved fuel economy. This means reduced rolling resistance and improved braking performance. So this one means increased friction. So in this case, you have to reduce the rolling resistance, but for the braking performance, you should increase the friction. But you can realize both of them because the frequency region of each phenomenon is different each other. And before think about it, you have to learn more about the measurement method to dynamic strain. So previously, I mentioned about the static method to measure the viscoelastic properties. So I elongated for constant length or constant stress. But when you think about the tire properties, the dynamic property is important. So frequency is important. So in that case, you can measure the mechanical property by using such a instrument. So in this case, you apply the dynamic strain to the sample. This part is lava. And from one side, when you apply the sinusoidal strain and measure the stress from this side, so you can know the elastic modulus or viscosity of the sample from the stress and strain dynamically. So when you think about the ideal elastic, if the material is ideal elastic material, so when you apply the strain like this, so the stress becomes like this. So as you know, the stress is proportional to strain. So the strain and stress is in phase. So both of them are cosine wave. But if the material is ideal viscous material, so the phenomenon becomes different from elastic one. In this case, when you apply the sinusoidal signal strain to the sample, in this case, stress is proportional to the strain rate. So strain rate is represented by like this sine wave. So this one is the cosine wave. So the strain and stress is not in phase. The phase difference becomes half pi. Okay? And the strain rate and the stress is in phase. So in this figure, in this plot, stress is represented by this color. And the strain rate, purple one, is proportional to the strain. No, stress. But the strain does not proportional to stress. And the relationship becomes like this. So when you apply the dynamic strain to the viscoelastic material, so this red one is stress for the viscoelastic material. But from this acknowledgement, you can understand the elastic component. Elastic component means the in-phase component with stress is elastic component. And the in-phase component with strain, strain rate is come from viscous property. So you can mathematically easily separate this signal to the proportional strings proportional component, black one, and strain rate proportional component, purple one. So when you get such properties, you can easily calculate the viscosity from this measurement. Viscosity can be represented by stress over strain rate, and elasticity can be shown by this one, stress over strain. But from these equations, you can see that the unit of viscosity and elasticity is different to each other. So in the case of dynamic measurement, in some case, you can calculate that, you can use not viscosity, but loss modulus. Loss modulus is calculated from the stress of the viscous component over strain. So this one has the same unit with elasticity because these are stress over strain. But the component is different to each other. This one comes from the elastic component, and this one comes from the viscous component. So this component is called as loss modulus. Okay. And one more thing. This slide is this introducing you color of the tire. And in this afternoon, Professor Nakajima will have also similar slide. But now I need to show you this one, so I'll explain here. And this picture is Toyota Automobile Museum's one. And this museum is located in Aichi Prefecture in Japan. And Aichi Prefecture is home of the Toyota Motor Corporation. And do you know why the color of the tire is black? Do you know? Maybe Professor Nakajima will also ask you the same thing, but please think about it. There's a reason why the tire is black. Okay, so I'll say the answer. So before 94, the tire color of the tire is not black. This one is white. But a person discovers the carbon black can reinforce the rubber and improves its durability. So after that, the carbon black is mixed with rubber, and that is used as for a tire. So normally now the tire, carbon black is used for tire. Okay, so under such a management, let's think about the tire performance. This one is the plot of the elasticity versus temperature. Okay, and this one, E prime means storage elastic modulus. So previously I forget to explain. So I showed you this equation and I explained this one is elasticity. But when you compare with loss modulus, you can say this one is storage modulus. So storage, so E prime is storage elastic modulus, and this one is E double prime is loss elastic modulus. And when you measure the tire's properties by using such a dynamic mechanical analysis equipment, you can get both parameters like this. And when you, in this case, the material is SPR, styrene butadiene copolymer. The chemical structure is like this. And when you use a low SBR, the elastic modulus is lower than the other one. And as I mentioned the previous slide, when you add carbon black, the blue one, elastic modulus increase. So the sample becomes more tough. Okay. So normally we use such kind of rubber composite or tire material, not the low SBR. And the important thing is energy loss. So loss elastic modulus is also related with energy loss. But normally when we think about the energy loss, the relationship between storage elastic modulus and loss elastic modulus is important. So we normally use the tan delta, value of the tan delta. Tan delta means E double prime over E prime. So ratio of the elastic modulus and storage modulus. So if the tan delta, that means relatively loss modulus is higher, the energy loss becomes higher. Okay, so from this data, you can easily get the plot of the tan delta like this. And in this case, the x-axis is temperature. Oh, and it's very difficult to explain, but normally, in the case of polymer, time temperature superposition principle is known. That means when you apply the stress, when you think about the behavior at the higher temperature, that corresponds to the behavior at lower frequency. So, and when you think about the lower property of the lower temperature, that corresponds to the higher temperatures behavior and then higher frequency behavior. Okay, so in such a based on in such a rule, the load resistance, rolling resistance property is related with tan delta of around 60 degrees Celsius. So this property is important for rolling resistance. So normally, the tan delta around this temperature is lower than this temperature. And around this temperature, the property relate with braking performance. So in this case, tan delta becomes higher around this temperature. This means energy loss becomes higher. So this is good for the braking performance. So when you stop the tire, the energy loss should be occur. But when you drive the car, the rolling resistance should be lower. So in this temperature region, the energy loss should be lower. And when you and this black one is that of low SBRs one. So low SBRs one is better for the braking performance. But it's better to add the carbon black to the tire because the durability of the tire becomes higher. But when you add the carbon black to the tire, the braking performance becomes lower, like this. So in these days, some of tire is not added the carbon black, but the silica is used. Silica is SiO2, so inorganic material. So when you add the silica nanoparticles to the tire, the braking performance becomes higher than the carbon black. And the rolling resistance of the silica one is lower than carbon black. So both are better than the carbon black one. So recently, such an investigation is improved, and some of the tire is made by using such materials. That is almost all of my lecture. And but I need to explain some of things to think about some.
Sorry for the interruption. It's
Yeah.
over 11 o'clock at Taiwan time. So
Yeah.
could the professor read up the speech? Thank you.
Oh, okay. But one thing I'd like to explain more things. So would you give me 1 or 2 minutes to explain?
Okay, that of course.
Okay. And when you think about the laboric materials for the application, you have to cross-link the rubber. So in the case of the isoprene, so when you cross-link the rubber, you can use sulfur to cross-link chemically. And if you don't cross-link the material, laboric materials, so laboric material, when you apply the stress, the laboric molecules can easily pass through each other, so elongate permanently. So it doesn't return to the original shape. So you need to make a chemical cross-link inside of the rubber molecules. So that's a very important point to utilize laboric materials when you apply this material either for the tire or the rubber ring or something. Okay, so that's all. Thank you.
All right. Thanks for the professor's speech. By the way, do you have homework for students?
Yes.
Or do you want to go to there, or I can share my screen here?
Would you show that one?
Or let me share my screen so you may probably explain your homework for students.
Okay, so
okay,
I'll explain. Yeah, okay, this one is
all right.
Homework. So homework is
this one, right?
This solves the equation. Yeah, I explained the Maxwell model in the slide, and you also get the main equations. But I didn't show the process to solve the equation. So please solve this equation and answer these 3 questions. Okay, that's all.
Oh, okay. Thanks for Professor Yama. And then this is the end of the morning lectures. And we will begin the afternoon's lecture at 1 o'clock in Taiwan time. So, or 2 o'clock in Japanese time. So thanks for students and the professors participation. Thank you.
Okay. Thank you very much.
See you in the afternoon.